Imagine looking up at the night sky and realizing that something entirely foreign, something that doesn't belong to our solar system, is quietly slipping past us, moving faster than anything we've ever seen up close. That's exactly what happened when astronomers spotted 3I Atlas, a visitor from deep interstellar space. At first glance, it looked like just another comet, the kind we've cataloged thousands of times before. But the closer scientists looked, the stranger it became. Its path wasn't the usual lazy loop of a solar system object. It was a hyperbolic escape route, proof that this thing came from beyond our sun's reach. And the speed? Over 130,000 miles per hour. It wasn't just drifting, it was tearing through space like it had somewhere urgent to be. For a brief moment, humanity caught sight of something alien, a piece of another world wandering into our backyard. And as the instruments locked on, the mystery only deepened. Instead of behaving like a comet, Atlas began releasing enormous clouds of gas, far more than its tiny body should have been capable of. A fog of carbon dioxide so massive it dwarfed the scale of Earth itself, as though the object were somehow alive, breathing out into the void. The discovery was thrilling, but also frustrating, because the timing of its journey couldn't have been worse. Just as excitement was building, Atlas began its approach toward the sun, slipping out of view for months and leaving scientists with only scraps of data to puzzle over. But even those scraps were enough to shake up everything we thought we knew about interstellar visitors. This wasn't just another comet. This was something different, something that challenged our models, taunted our understanding, and raised questions that no one yet had the courage to fully answer. On July 1st, 2025, astronomers in Chile scanning the night sky with the Atlas survey telescope picked up something that didn't quite fit. At first, it was logged as just another faint object moving across the stars, one of the countless icy fragments drifting through the solar system. But within hours, careful tracking revealed something unusual. Its orbit was unlike anything local. Instead of circling the sun like the planets and comets we know, this object was on a one-way trajectory, slicing through our system on a hyperbolic path that meant only one thing. It wasn't from here. This was an interstellar visitor, a body that had spent millions, maybe billions, of years wandering the galaxy before fate sent it skimming past our sun. Almost immediately, scientists knew they had stumbled on something extraordinary. It was only the third time in history humanity had confirmed such an object, following Oumuamua in 2017 and Borisov in 2019. And already the data suggested that this new arrival, named 3I, or the third interstellar object, and nicknamed Atlas after the survey that found it, was going to be even stranger than its predecessors. The first hint of just how strange came from its sheer velocity. When astronomers ran the calculations, they realized Atlas was tearing through space at an astonishing 130,000 miles per hour. To put that in perspective, the fastest spacecraft humans have ever built struggled to reach even a fraction of that speed. Atlas was moving so quickly that Earth's gravity barely tugged on it, unable to pull it into any kind of capture. It was a brief visitor, passing through like a ghost on a mission, and once it left, there would be no chance of following. That urgency made every observation critical because scientists had only a narrow window to study it before it vanished into the void forever. At first, telescopes focused on the object's nucleus, the solid core that makes up the body of a comet. What they found was puzzling. The nucleus appeared incredibly small, much smaller than expected for something releasing the kind of light and gas seen in early detections. Instead of behaving like a frozen chunk of ice, Atlas began showing bursts of activity, far too powerful for its size. Carbon dioxide streamed from it in enormous quantities, forming a cloud so vast that its scale defied belief. To give an idea, the haze around Atlas grew larger than the orbit of the moon around Earth. For something so tiny, it was like watching a matchstick light up a bonfire. But this wasn't just about spectacle. It was about physics, and the numbers didn't add up. Normally, comets release a mixture of water vapor, carbon monoxide, and carbon dioxide when they heat up near the sun. These gases form the familiar glowing coma and tail we see in classic comet images. But Atlas wasn't following the rules. Instead, it was producing carbon dioxide at a ratio almost 8 times higher than water, a complete reversal of the pattern we see in typical comets from our own solar system. That ratio suggested something fundamental. Atlas hadn't formed under the same conditions as the icy bodies orbiting our sun. It was born in a different star system, under different chemistry, carrying with it the fingerprint of an alien origin. For astronomers, that realization was electrifying. Here was physical evidence drifting right past us of how other planetary systems might look. But alongside the thrill was confusion, because the numbers raised more questions than answers. Why was Atlas so rich in carbon dioxide? Why did it release gas in such massive, sustained outbursts? And perhaps most importantly, why did its behavior defy the models that had worked so well for comets closer to home? The timing of its discovery only added to the drama. After being spotted in July, astronomers knew Atlas would make a close approach to Mars on October 3rd, 2025, offering the perfect chance for spacecraft orbiting the red planet to snap pictures. But almost immediately after that, Atlas would swing behind the sun, vanishing from Earth's view for nearly 2 months. In other words, just as interest was heating up, the universe seemed determined to hide its secrets. Scientists scrambled to gather every piece of data they could before that blackout period began, coordinating a massive international effort with observatories around the world, from Hawaii to Spain, Chile to space telescopes like Hubble and the James Webb. The global astronomical community turned its eyes toward the new interstellar wanderer. For once, competition gave way to urgency as everyone realized this was a once in a lifetime opportunity. Even the early images were haunting. Hubble revealed a faint but beautiful coma stretching thousands of miles, wrapping the tiny nucleus in a veil of dust and gas. Gemini North, one of the most powerful ground based telescopes, confirmed the presence of an elongated tail, though it appeared later than expected. Instead of the steady, predictable tail of a comet, Atlas seemed hesitant, like it was holding something back. Some scientists described it as though the object were alive, breathing slowly, exhaling clouds in fits and starts, responding not just to the sun's heat, but to some internal rhythm no one understood. That poetic description captured the mystery perfectly. This was not just an object, it was an enigma unfolding in real time. The speed at which it moved added to the sense of fleeting wonder. Every night, it shifted noticeably against the background stars, a reminder that it was only passing through. Unlike planets or familiar comets that return on long cycles, Atlas would never come back. Its path was clear. It entered the solar system from interstellar space, swung around the sun, and would soon shoot back out, continuing its journey into the dark. There would be no second chance. The urgency pushed observatories to unprecedented levels of cooperation. NASA's Swift telescope monitored its ultraviolet glow. JWST prepared to parse its chemical signature, and the European Space Agency worked out observation strategies for their own instruments. It wasn't just about cataloging a comet, it was about peering into another planetary system without ever leaving our own. And yet, for all the excitement, Atlas remained a source of frustration. Its nucleus was so small and faint that estimates of its size varied wildly, anywhere from a modest city block to something closer to a mountain. Without knowing its exact rotation speed or axis, astronomers struggled to model its behavior. Some argued it might be spinning so slowly that its outgassing came in sudden bursts rather than steady flows. Others suggested its spin was aligned in such a way that the sun lit only specific vents at certain times, but these were educated guesses, nothing more. The truth was that Atlas refused to reveal itself fully. It was the ultimate tease, showing just enough to get under our skin, but not enough to solve the puzzle. Still, the discovery lit a fire in the scientific community. This was only the third confirmed interstellar object in history, and already it was showing us that every one of these visitors seemed radically different. Oumuamua was a cigar-shaped rock that accelerated in ways no comet should, with no visible tail. Borisov was a comet-like traveler, far richer in carbon monoxide than usual, and now Atlas arrived, carrying with it a bizarre dominance of carbon dioxide, behaving like something in between a comet and a mystery. Three visitors, three entirely different personalities, as if the universe were deliberately reminding us that our solar system is just one flavor among countless others. The discovery phase of Atlas was more than science. It was a moment of perspective. Watching this faint alien traveler glide past us, we were reminded of just how small we are in the cosmic scheme. Here was an object that may have formed around a star billions of years ago, ejected during some long forgotten planetary collision, and left to wander the galaxy until by chance it brushed close enough to our sun for us to notice. It was like a message in a bottle drifting across an ocean of stars, and for a brief window, we were the lucky ones to find it. Whether we understood the message or not was another matter entirely. When Atlas first revealed itself, astronomers thought they were simply witnessing the behavior of another interstellar comet, perhaps a little odd, but nothing that would rewrite the rulebook. But then came the data that made everyone stop and rethink. The object wasn't just active, it was impossibly active. For something so small, Atlas should have been limited in how much gas it could release. Yet it was producing immense clouds of carbon dioxide at a rate that dwarfed anything scientists had expected. Normally, when a comet approaches the sun, it begins to warm up and release gas as its frozen ices sublimate into vapor. These jets of water vapor, carbon monoxide and carbon dioxide, are predictable. And while they can produce magnificent tails and halos, the underlying chemistry is well understood. But Atlas wasn't following those rules. Instead of a balanced mixture dominated by water vapor, the ratio was completely skewed, with carbon dioxide outnumbering water by an incredible 8 to 1. This wasn't just unusual, it was unheard of. The effect of that imbalance was dramatic. The coma, the hazy shroud of gas and dust surrounding the nucleus, expanded to a size that almost defied comprehension. Some estimates placed its extent at more than 1 million miles across, meaning that the cloud surrounding this tiny body was larger than the orbit of Earth's moon. To think of something so small, generating something so vast, strained the imagination. It was as if Atlas had lungs the size of a planet, exhaling with each moment it was bathed in the sun's heat. The sheer volume of gas pouring out suggested either an extraordinary composition or a mechanism of release that scientists had never before observed. As the observations piled in, the words anomalous and mysterious began appearing again and again in reports. One team noted that the level of carbon dioxide could only be explained if the object's surface were unusually rich in frozen CO2, something not seen in our local comets. Others suggested that perhaps the gases were trapped beneath the surface, only to burst out explosively once the crust cracked under solar heating. Still others began whispering about stranger possibilities, speculating whether chemical processes we hadn't yet understood or even electromagnetic interactions could be at play. Whatever the cause, the bottom line was clear. Atlas was behaving in ways that didn't match any of our models. The strangeness didn't stop at chemistry, its physical behavior added another layer to the puzzle. The object's nucleus was too faint for telescopes to pin down precisely, leaving astronomers unsure whether it was the size of a skyscraper or a small city. Yet its activity suggested something much larger, as though it were punching above its weight in terms of energy output. Even more frustrating, its rotation was a blank mystery. Normally, the spin of a comet can be detected by variations in the brightness of its light curve as different parts of its surface face the sun and vent gas. But Atlas refused to show any obvious pattern. Was it spinning too slowly to register? Was it aligned in such a way that its vents stayed constantly exposed to the sun? Or was its surface so evenly active that no changes showed up? Each explanation led to more questions, and none offered a satisfying answer. The closer scientists looked, the less Atlas resembled the neat textbook examples of comet behavior they had grown up studying. Its tail was another oddity. Rather than developing immediately as it approached the sun, the tail seemed hesitant, appearing later than expected and growing in strange fits. At times, it seemed to flare up dramatically, then quiet down, as if the object were reluctant to commit to the classic cometary appearance. When the tail did develop, its shape was oddly diffuse, less the sharp, elegant streamer of a standard comet, and more a hazy extension of its massive gas cloud. Once again, the data refused to fit the models. For the scientists watching in real time, this was both thrilling and maddening. On the one hand, Atlas was teaching us that interstellar objects are far more diverse than we ever dreamed, carrying the fingerprints of alien environments and histories. On the other hand, every attempt to pin it down only seemed to deepen the mystery. Its behavior was impossible by the standards of our current understanding, and that impossibility forced the astronomical community to confront just how little we really know about the frozen wanderers that drift between stars. Adding to the intrigue was the way Atlas's activity seemed to defy its size and presumed mass. Normally, when a comet loses gas at such extreme levels, the resulting jets cause noticeable changes in its motion, tiny accelerations that can be measured with precise tracking. This phenomenon was famously observed with Oumuamua, which appeared to accelerate without a visible tail, sparking wild speculation about its true nature. With Atlas, the outgassing was unmistakable, and yet, at least so far, no strange accelerations had been confirmed. It was venting enough material to envelop planets, but somehow maintaining a stable trajectory. That contradiction gnawed at scientists. Was the acceleration simply too subtle to detect yet? Or was there something about its gas release that balanced itself like a rocket firing in two opposite directions at once? Every explanation felt provisional, a placeholder until more data could be collected. The impossible behavior of Atlas extended beyond the numbers into the realm of perception. For many astronomers, the object seemed almost alive, not in the literal sense, but in the way its activity suggested intent. It didn't just release gas, it exhaled in waves, almost rhythmically, as though something deep within the body pulsed with energy. Of course, no one seriously believed it was alive, but the metaphor stuck, and even in professional papers, the language took on an almost poetic edge. There was something haunting about watching this alien fragment breathe out clouds that dwarfed entire worlds, drifting across the solar system like a phantom. The mysteries piled higher when spectroscopic studies came in from the James Webb Space Telescope. Webb, with its unmatched ability to parse chemical fingerprints, confirmed the staggering imbalance between carbon dioxide and water. The ratio was not just unusual, but unprecedented, challenging the very assumptions about how ices form around stars. In our solar system, water ice dominates because of the sun's temperature profile during the early stages of formation. If Atlas carried so little water and so much CO2, then it must have formed in a drastically different environment, perhaps around a cooler star or in the distant reaches of a system where water never condensed in large amounts. That meant Atlas wasn't just a curiosity, it was a clue, a direct sample of alien chemistry drifting through our skies. And yet, even as Webb revealed more, it also added to the enigma. Some instruments detected faint signs of water after all, while others failed to find any trace. The conflicting results suggested that Atlas might have an uneven composition with pockets of water hidden beneath layers of CO2, or perhaps the water was being released in such small bursts that it was easy to miss. The inconsistency frustrated researchers, but it also hinted at complexity. Atlas wasn't a simple frozen relic, it was layered, dynamic, and resistant to easy categorization. As weeks turned into months, the sense of wonder grew. Atlas wasn't just another object, it was a cosmic puzzle piece, one that refused to fit the board we thought we understood. Its impossible behavior forced scientists to re examine assumptions, rewrite models, and acknowledge that interstellar visitors are not bound by the rules of our solar neighborhood. Each outburst of gas, each unexpected fluctuation was a reminder that the universe is stranger than we often allow ourselves to imagine. For those following its path, there was a sense of awe tinged with urgency, because soon enough, Atlas would slip behind the sun, vanishing from view and leaving only questions in its wake. But perhaps the most haunting thought was this: if Atlas was only the third interstellar object we'd managed to spot, and each of those three was utterly unique, then what else is out there? How many more impossible wanderers drift through the galaxy, carrying secrets from alien suns, waiting to cross paths with us? And when the next one arrives, will we finally be ready to chase it, or will we once again be left watching helplessly as it vanishes into the dark? From the very beginning, one of the most unsettling things about Atlas was not just its chemical oddities, but its path through the solar system. The orbit it traced out across the stars was so alien, so precise, that it left many astronomers uneasy. Most comets we know come in on elongated ellipses, looping around the sun like returning travelers before swinging back out, destined to revisit after decades or centuries. But Atlas wasn't looping back. Its trajectory was hyperbolic, a graceful arc that would bring it close to the sun only once before casting it back into the infinite. That alone was enough to confirm its interstellar origin, but the details of the path were even more intriguing. It moved as though guided by a ruler, cutting through the solar system with a clarity and speed that made Earth's own orbit look almost clumsy. The mathematics of its orbit suggested it had entered our system millions of years earlier, silently coasting through the void until it finally came within range of our instruments. That idea that it had been drifting near us unnoticed for so long was eerie in itself. The first major milestone in its journey was its close approach to Mars, scheduled for October 3rd, 2025. Astronomers marked the date with anticipation because it meant that orbiters around the red planet, including NASA's Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter, might be able to capture unique views of the interstellar traveler. Unlike Earth based telescopes, which were already straining to see its faint light against the glare of the sun, instruments near Mars would have a cleaner vantage point. The hope was that these spacecraft could provide images of its nucleus and coma during a critical moment in its passage. It was a rare alignment, almost too perfect, as though the cosmos itself had staged an encounter. But that sense of perfection came with a cruel twist. Just weeks after passing Mars, Atlas would vanish behind the sun, slipping into a period of invisibility that astronomers called solar conjunction. For nearly 2 months,
No Earth based telescope would be able to track it. The timing could not have been worse. The sun's blinding light would mask it completely, leaving the scientific community with nothing but speculation until it reemerged. And yet, that period of darkness was also tantalizing. Atlas was expected to reach its perihelion, its closest point to the sun during that hidden interval, whatever secrets it had to reveal about its activity, its gas release, and perhaps even its stability would happen while it was out of sight. It was as if the universe had pulled a curtain across the stage at the very moment of climax, forcing everyone to wait for the reveal. Some joke that Atlas had a flair for the dramatic, arriving with strange chemistry, building anticipation, then disappearing for an intermission just when curiosity was at its peak. But the trajectory held more mysteries than timing alone.
Its hyperbolic escape path suggested that Atlas hadn't been ejected from some nearby system recently. It had been wandering the galaxy for perhaps hundreds of millions, if not billions of years. That long journey raised unsettling questions. How had it survived intact for so long? Most small bodies are battered, broken, or eroded by cosmic rays during interstellar travel. Yet Atlas, though active, seemed to hold together, venting gas in impossible volumes, but never shattering completely. Its resilience against the violence of space suggested a toughness not easily explained. And then there was the matter of precision.
Its approach through the solar system seemed almost scripted. While it was certainly the result of pure celestial mechanics, the way its trajectory lined up for maximum visibility before disappearing felt uncanny, as if designed to toy with our instruments and our patience. Astronomers were particularly struck by how close Atlas would skim to the sun. At perihelion, its distance would shrink to less than that of Mercury, placing it under extreme solar radiation and heat. Many comets simply disintegrate under such stress, breaking apart into fragments that scatter and fade. Whether Atlas would survive was an open question.
And the possibility of fragmentation made its path even more compelling. If it shattered while behind the sun, the debris could scatter along its outbound path, creating a trail that telescopes might pick up once it emerged. Such an event would be a scientific windfall, offering a chance to study interstellar material in unprecedented detail. But it also carried a note of sadness. If Atlas broke apart, we would lose the chance to study it as a coherent, intact messenger from another system. Its strange trajectory was a race against time, an opportunity that might collapse into dust before our eyes.
Adding to the intrigue were subtle irregularities in how the trajectory was modeled. Although no definitive non gravitational acceleration had been confirmed, small deviations in its orbit hinted that something unusual might emerge during perihelion. Astronomers remembered all too well the strange acceleration of Oumuamua, which had defied explanation and fueled theories of exotic propulsion. With Atlas, they watched nervously for signs of a repeat. The intense outgassing of carbon dioxide should, by all logic, nudge its orbit in measurable ways. If those nudges matched predictions, the mystery would be one of chemistry. But if the deviations grew erratic or inexplicable, comparisons to Oumuamua would return with a vengeance. The very idea that two of the three interstellar objects detected so far might share such bizarre traits was enough to keep astronomers awake at night. Yet, even as they braced for anomalies, the elegance of Atlas's trajectory left many in awe. There was something profoundly humbling about watching an object that had traveled across light years sweep effortlessly through our solar system, ignoring the gravitational pull of planets and stars alike, gliding as though nothing could slow it down. For observers,
It was a reminder that our sun, so dominant to us, was just another waypoint in a much larger cosmic journey. Atlas's path was a line across the galaxy, and our entire solar system was nothing more than a brief stop along the way. Public fascination grew as the media picked up the story. Headlines described Atlas as a cosmic interloper and a galactic visitor, framing its trajectory as though it were a character in a drama. The idea that it was just passing through, never to return, lent it a ghostly quality. Some compared it to a shooting star stretched out over months, a fleeting miracle you had to catch before it disappeared forever. For scientists, that metaphor wasn't far from the truth. The strange trajectory made clear that once Atlas left, it was gone for good. There would be no return orbit, no second pass. Humanity had one chance to watch, to measure, to learn, and then the moment would be gone, carried away on a path into endless night. In the end, the strange trajectory of Atlas wasn't just a matter of orbital mechanics. It was a narrative in itself, a story written in mathematics and motion. It came at us from nowhere, crossed paths with Mars, teased us with visibility before vanishing behind the sun, and promised to reemerge transformed or broken, on its way out of reach forever. Every arc of its path was layered with meaning, a reminder that the universe is filled with wanderers whose journeys are written long before we ever see them. Atlas's trajectory was strange because it wasn't ours. It belonged to another system, another history, another time. And for a fleeting moment, that history crossed ours, leaving us with questions that may never fully be answered. The moment telescopes around the world and in orbit turned their gaze toward Atlas, the sense of anticipation was electric. Humanity had seen interstellar visitors before, but this one carried with it a particular kind of mystery, already whispering through the data in its chemical imbalance and its strange trajectory. What everyone wanted was a clear look, an image that could strip away some of the uncertainty and show us exactly what this alien traveler looked like. And so the call went out for the most powerful instruments we had, and the first images began to arrive. They weren't the kind of sharp photographs you'd find in a glossy magazine. They were faint, carefully processed smudges of light against the dark. Yet within those smudges, a whole new chapter of the story unfolded.
Hubble was one of the first to capture Atlas, and what it revealed was astonishing. Instead of a neat, compact nucleus with a small halo of gas, the images showed a tiny pinprick of brightness surrounded by a massive, diffuse coma stretching thousands of miles into space. It looked less like a comet and more like a glowing ember caught in a fog, a fragile core barely visible within the haze. Scientists had expected activity, but not on this scale. The coma was vast compared to the nucleus, suggesting that the little body inside was venting far more material than it had any right to. If you looked only at the coma's size,
You might assume the nucleus was enormous, perhaps comparable to some of the great comets in our solar system's past, but in reality, the core appeared far too small to justify the spectacle, as though the universe had staged an optical illusion designed to confound. From Gemini North in Hawaii came further revelations. This giant ground based telescope, with its sensitive instruments and adaptive optics, offered another perspective on the alien visitor. Gemini confirmed what Hubble had hinted at. The coma wasn't just large, it was complex. Its brightness varied subtly across different regions, suggesting uneven activity across the nucleus. Some areas seemed to flare with gas and dust, while others stayed comparatively quiet, giving the whole object an irregular, almost alive quality. Even more curious was the tail. Normally, comets sprout their tails as soon as solar radiation begins driving sublimation, a steady stream that forms a sharp and predictable line away from the sun. Atlas, however, seemed reluctant to reveal one. Its tail appeared later than expected, faint and understated at first, as though it were struggling to keep pace with the intensity of its own gas release. When the tail did emerge,
it wasn't the crisp streamer familiar from textbook comet photographs, but a diffuse extension of the coma itself, a hazy elongation that resisted definition. These early images captured more than just data, they captured imaginations. The faint photographs circulated widely, accompanied by artist impressions that attempted to illustrate what the numbers meant. Some depictions made Atlas look like a glowing ghost, a pale sphere exhaling mist into the darkness. Others portrayed it as a fragile ember racing through the void. For the public, these interpretations were enough to spark fascination, but for scientists,
The raw data was even more compelling. What they saw in those fuzzy smudges challenged every assumption about how a comet should behave. One detail in particular stood out: the nucleus itself. Despite all the activity, the core remained stubbornly elusive. Telescopes strained to pin down its size, but the surrounding coma overwhelmed the view. Estimates varied wildly, from as small as a few dozen meters across to as large as several kilometers. Such uncertainty was frustrating because the size of the nucleus would determine how much material it could possibly hold and how long it could sustain its furious outgassing. A smaller nucleus would mean it was punching far above its weight, expelling matter at a rate that defied logic. A larger nucleus would explain the activity more easily, but then why did it appear so faint? The paradox deepened the sense of impossibility. Hubble's ultraviolet imaging added another layer to the mystery. It revealed not just the size of the coma, but its composition, confirming the dominance of carbon dioxide over water. The spectral data lined up with what other instruments had already suggested, painting a picture of an object fundamentally different from the icy wanderers of our own solar system.
this wasn't a local comet gone rogue. It was a foreigner carrying with it the chemical fingerprint of an alien nursery. To see that fingerprint in real time in the faint light captured by Hubble's sensors was to hold in our hands a direct message from another star system. And yet the message was written in a language we barely understood. Gemini's observations helped refine the story, showing that the coma wasn't static but dynamic. Jets of gas seemed to shift, brightening and fading as though the nucleus were exhaling in bursts. Some astronomers described it as rhythmic.
Though whether that rhythm was the result of rotation or some deeper process was impossible to say. The idea that Atlas was breathing became a recurring metaphor, one that blurred the line between scientific detachment and poetic awe. It wasn't just an object, it was a performance, and we were its audience, watching from across millions of miles. What made these first images even more profound was the context. This was only the third interstellar object humanity had ever seen, and the first to be imaged in such detail. With Oumuamua, telescopes had only captured faint light curves, leaving its true shape a matter of debate and speculation. With Borisov, the activity had been more familiar, resembling that of solar system comets, though with odd chemical twists. But with Atlas, we had direct images of something that defied comparison. Every smudge of light carried with it a sense of history, a tangible piece of another world drifting through ours. The photographs weren't beautiful in the traditional sense, but they were historic, a visual record of humanity's fleeting encounter with an interstellar stranger. As the data rolled in, the frustration of imperfection mingled with the thrill of discovery. Astronomers wanted more clarity, sharper images, undeniable measurements. But the reality of observing something so faint, so distant, and so transient and compromised, the images were messy, incomplete, often open to interpretation. Yet that incompleteness was part of the allure. Atlas refused to let us see it plainly, hiding behind its own fog, teasing us with glimpses while keeping its core secrets intact. It was a reminder that the universe rarely gives up its mysteries easily. For many scientists, the most haunting part of those first images was the scale of the coma. To think that a speck of ice and rock, no larger than a mountain at best, could generate a shroud larger than Earth itself was almost incomprehensible. It spoke to forces we barely understood, to compositions and processes shaped under alien suns. Looking at the photographs, it was easy to forget that the glowing cloud was not the object itself, but merely the breath of something far smaller, hidden deep within. That duality, the tiny seed and the vast fog it created, made Atlas one of the most captivating astronomical subjects of its time. As the world studied those images, the question loomed: what more would Atlas reveal when it grew closer to the sun? Would the coma swell to even greater proportions?
Blanketing entire regions of space in its alien chemistry? Would the nucleus fracture under the strain, splitting into shards that drifted apart like cosmic breadcrumbs? Or would it hold together, carrying its secrets with it as it disappeared into the dark? Each photograph was a promise, a cliffhanger that pointed to mysteries yet to come. And as the object moved steadily along its strange trajectory, one truth became impossible to ignore. The more we saw of Atlas, the less we understood it. If the first images of Atlas raised eyebrows, the chemical analysis delivered by the James Webb Space Telescope dropped jaws. Hubble and Gemini had shown us its strange, hazy figure, but Webb, our most advanced eye on the universe, cut straight into the composition of the gases it exhaled. Scientists knew to expect surprises, but nothing could have prepared them for the sheer scale of what Webb uncovered, where most comets we know breathe out water vapor as their main ingredient. Atlas seemed to laugh the rules, releasing clouds of carbon dioxide so immense and so dominant that water barely showed up in the readings. The ratio was shocking: 8 parts carbon dioxide to every 1 part water. That imbalance wasn't just odd, it was unheard of in our solar system. It was as if Atlas had come from a completely different recipe book of planet formation, carrying a chemical fingerprint that shouted, "I am not from here." Webb's instruments confirmed what ground based telescopes had only hinted at: the size of the carbon dioxide cloud dwarfed comprehension. Imagine a bubble of gas stretching farther than the distance between Earth and the moon. That wasn't an exaggeration, it was reality. A nucleus perhaps no bigger than a small mountain was somehow flooding space with a cloud on a planetary scale. It was like watching a single candle fill a stadium with smoke. The sheer mismatch between the size of the body and the scope of its emissions confounded every model. How could something so small generate something so enormous? Some speculated that the nucleus was riddled with fractures, vents opening everywhere like the pores of a sponge, each one leaking carbon dioxide. Others wondered if the gas wasn't just on the surface, but buried in deep reserves, built up over billions of years, and now bursting free in a sudden release. But there was no consensus, only awe. The lack of water added another layer of mystery. In our solar system, comets are sometimes called dirty snowballs because water ice is their dominant component. Atlas, however, seemed to be a dirty, dry ice ball, something fundamentally alien in its makeup. That composition alone suggested it had formed in an environment unlike anything we've seen. Perhaps it was born far from its parent star in regions so cold that water was scarce but carbon dioxide could freeze easily. Or perhaps its home system had a chemical profile unlike our own, rich in CO2 and poor in H2O. Whatever the origin, Atlas was a messenger from a place with rules different from ours.
Carrying with it a story of planetary formation written in strange chemistry. As Webb gathered more data, contradictions began to appear. Some instruments hinted at faint traces of water after all, though at levels almost negligible compared to the carbon dioxide flood. Other observations failed to find water at all, suggesting inconsistencies or uneven release. It was possible that Atlas contained patches of water ice buried beneath the surface, emerging only sporadically when fractures allowed sunlight to penetrate. Or maybe the water had already been depleted during its long interstellar journey, leaving only the more resilient carbon dioxide to dominate. The conflicting evidence painted a picture not of simplicity, but of complexity, as though Atlas were layered, its interior hiding secrets that no telescope could fully expose. The implications were profound. If Atlas truly lacked significant water, it might mean that interstellar objects are far more chemically diverse than anyone imagined. The first two we had seen already told us as much. Oumuamua behaved like nothing we'd ever encountered, showing no tail, but still accelerating mysteriously, while Borisov looked more familiar, yet was loaded with carbon monoxide, far beyond our norms. Now Atlas arrived, dripping carbon dioxide in unprecedented amounts, flipping our expectations upside down. Three interstellar objects, three completely different chemistries. It was as though each one carried a sample kit from a different corner of the galaxy, proof that the diversity of planetary systems is beyond anything our imaginations had prepared us for. The shock of Webb's data reverberated beyond the scientific community. The public, already captivated by Atlas's ghostly images, seized on the idea that it was chemically alien.
Headlines described it as a carbon dioxide comet, a phrase that undersold the scale of the discovery but captured the imagination nonetheless. Science communicators compared it to finding a new species of life, one that shared the general shape of something familiar but whose biology was entirely foreign. Atlas wasn't just another comet, it was a window into a different kind of solar system, one whose icy leftovers had a recipe utterly unlike our own. And still the questions piled up. Why was Atlas releasing so much carbon dioxide so easily? Was it simply composition, or was some unknown process at work?
Some researchers proposed exotic mechanisms. Perhaps its ices were mixed with other compounds that destabilized them, triggering runaway sublimation. Others speculated that the object might have undergone heating in its parent system that altered its chemistry in ways we didn't yet understand. The boldest voices suggested that maybe our categories of comet and asteroid were inadequate for interstellar material, that Atlas belonged to a class of objects entirely outside our framework. For every hypothesis, counter-arguments sprang up, but one truth was undeniable. Atlas refused to be explained away.
What made Webb's contribution particularly powerful was the precision of its instruments. Unlike ground based telescopes, which must peer through Earth's atmosphere and its distortions, Webb operated from the cold clarity of space. Its infrared sensors could pick out the faintest signals, teasing apart the fingerprints of different molecules. In the case of Atlas, those fingerprints were written in bold strokes of carbon dioxide, repeated and reinforced across multiple observations. The certainty of the data left no wiggle room. This wasn't a glitch or a misreading, it was real, and it demanded explanation. Astronomers began comparing Atlas's chemical shock to Oumuamua's mysterious acceleration. With Oumuamua, the lack of visible outgassing had fueled wild speculation, from exotic hydrogen icebergs to even more exotic ideas of artificial origin. With Atlas, the opposite problem emerged. There was no shortage of gas, but the wrong kind, in the wrong proportions, released in overwhelming quantities. Where Oumuamua was a silent enigma, Atlas was a noisy one, screaming its alien chemistry into the void. Both were puzzles, and together they painted a picture of interstellar debris that was far stranger than anyone had dared predict.
As Webb continued to watch, the coma expanded further, its edges blurring into the background of space. The sheer scale made Atlas seem less like a solid body and more like a phenomenon, a diffuse entity whose physical boundaries were impossible to define. In a sense, that's exactly what it was: a tiny nucleus wrapped in an atmosphere of its own making, a self generated planet sized aura drifting across the solar system. The irony wasn't lost on anyone. Here was an object smaller than a city, cloaked in a shroud, larger than planets, outgassing in a way that defied comprehension. The chemical shock forced a shift in perspective.
No longer could astronomers think of interstellar visitors as curiosities or outliers. Each one seemed to represent a unique environment, a unique history, a unique chemical fingerprint. Taken together, they suggested that the galaxy is littered with diversity, each star system cooking up its own strange recipe of ices, rocks, and gases. Atlas wasn't just teaching us about itself. It was teaching us about the broader cosmos, about the infinite variety of worlds and processes that shape them. And perhaps the most tantalizing aspect of all was what might come next. Atlas hadn't yet reached its closest approach to the sun when Webb captured its chemical fingerprint. The real fireworks were still ahead, hidden behind the solar glare during its conjunction. Would the carbon dioxide outgassing grow even more intense? Would hidden reservoirs of water suddenly erupt, altering the balance? Would the nucleus crack under the strain, breaking apart into fragments that would each carry their own chemical story? The uncertainty was maddening, but it was also thrilling. For once, humanity was watching in real time as an alien world revealed itself, layer by layer, out in the open sky. For all the data, the images,
And the measurements pouring in from the world's most powerful observatories, Atlas remained cloaked in mystery. Every discovery opened the door to another question. Every answer revealed deeper uncertainty. What we didn't know about this strange interstellar traveler was, in many ways, more compelling than what we did. And that ignorance wasn't a sign of scientific failure. It was a sign of just how far outside the familiar this object truly was. One of the biggest unknowns was the size of its nucleus. Astronomers strained to measure it, using light curves and indirect methods, but the truth stubbornly refused to emerge.
some estimates suggested it could be no bigger than a building, a frozen shard smaller than a city block, while others argued it might stretch several kilometers across, more like a modest mountain. That kind of uncertainty would be laughable for most solar system comets we've studied up close, but with Atlas, it was unavoidable. The coma was simply too overwhelming, flooding the instruments with its brightness and masking the tiny core at its heart. Without a clear picture of the nucleus, scientists were left guessing about the basic parameters of the object's mass, density, and lifespan.
A small body spewing such vast clouds of carbon dioxide would burn itself out quickly, while a larger one might sustain the activity for longer. Which was it? No one could say for certain, and the ambiguity gnawed at every model. Closely tied to the question of size was the mystery of its rotation. Normally, a comet's spin reveals itself in the way its brightness changes over time as different sides face the sun and release jets of gas. Those fluctuations can be charted like a heartbeat, giving scientists a sense of how fast the body spins and how its vents are distributed. But Atlas defied detection. Its light curve was eerily flat.
Showing no obvious signs of rotation at all. Was it spinning so slowly that no changes registered? Was its axis aligned in such a way that the sun illuminated the same regions constantly, creating a steady glow? Or was it so uniformly covered in vents that every part looked the same? Each possibility was strange, but none could be confirmed. The silence of its spin left the unsettling impression that Atlas was more stable, more constant than any comet had a right to be. Some even wondered if its shape might be a factor, perhaps elongated like Oumuamua, or unusually spherical, making it harder to track changes. The absence of evidence here was almost as loud as a discovery itself. a blank space that forced astronomers to admit how little they really knew. Then there was the puzzle of its water, or the lack of it. Webb's instruments had hinted at faint traces, while others saw none at all. The contradiction raised possibilities that were equally fascinating and frustrating. If Atlas contained little to no water, then it represented a type of icy body alien to our solar system, formed in conditions we've never seen. But if water was present in hidden reservoirs, then why wasn't it venting more visibly? Was it buried under layers of carbon dioxide?
Shielded from the sun until deeper fractures opened, or had it already been depleted during its long interstellar journey, lost to cosmic rays and micrometeorite impacts over millions of years? Without a definitive answer, we were left staring at a paradox, a comet that seemed to be both wet and dry, both rich in ice and devoid of it, depending on which data set you trusted. The behavior of its tail deepened the enigma. Instead of the familiar sweeping arc of a comet's dust trail, Atlas's tail appeared faint, hesitant, and oddly diffuse. At times, it seemed to vanish altogether, swallowed up by the massive coma. At others,
It stretched in directions that didn't quite match predictions, as though the object were shrugging off the sun's influence in unpredictable ways. Some speculated that electromagnetic forces might be shaping the tail in unusual patterns, interacting with the solar wind in ways we hadn't modeled. Others suggested that the sheer dominance of carbon dioxide over water was producing different dynamics in the dust grains carried along. But again, the data was incomplete, the interpretations provisional. The tail was there, but it wasn't playing by the rules, and that left scientists scratching their heads. Even the question of Atlas's structural integrity remained unresolved. Would it hold together during its close pass around the sun, or would it shatter under the heat like so many comets before it? Predictions varied wildly. Some argued that its vigorous outgassing would weaken it, carving fractures that would inevitably split it apart. Others thought its long interstellar journey might have hardened it, baking its surface into a crust tough enough to withstand the stress. The truth wouldn't be known until perihelion, and by then the object would be hidden behind the sun, out of our sight. The suspense was unbearable, a cosmic cliffhanger in which the fate of an alien visitor would be decided while no one could watch. Adding to the list of unknowns was the question of Atlas's true origin. We knew it came from interstellar space, but from where exactly? Its trajectory could be traced backward, but the trail grew faint and uncertain the further you went. Over millions of years, the gravitational nudges of stars and galactic tides blurred its past into obscurity. Some models suggested it might have come from the thick disk of our galaxy, a population of ancient stars billions of years old. If that was true,
Atlas might predate Earth itself, a fossil from an earlier era of planetary formation. Others argued it could have been ejected from a relatively nearby system, one whose architecture had sent it hurtling into the void without a clear fingerprint to trace. Its birthplace remained a mystery, a reminder of how vast and unknowable the galaxy can be. Even more tantalizing was the question of how common objects like Atlas really are. If this was only the third interstellar visitor we'd spotted in less than a decade, did that mean such objects are constantly drifting through our system, most too faint to see? Or was it a statistical fluke, a lucky alignment of discoveries made possible by modern telescopes? The answer could reshape our understanding of the galaxy. If interstellar visitors are common, then the solar system is regularly bathed in the debris of other worlds, each piece carrying alien chemistry and history. If they're rare, then each one is a precious chance event, a fleeting encounter that may not happen again for centuries. Which was it? We didn't know, and the uncertainty was as thrilling as it was humbling. Perhaps the most haunting unknown was whether Atlas might reveal anomalies in its motion, the kind that had made Oumuamua infamous. So far,
No unexplained accelerations had been confirmed, but with the level of outgassing it displayed, many believed it was only a matter of time before irregularities appeared. If those irregularities matched expectations, then the mystery was chemical. But if they didn't, if Atlas began to move in ways no model could explain, then we would be thrust once again into the uncomfortable territory where science meets speculation. The possibility hung over the entire enterprise, unspoken in the most cautious papers, but whispered in the back rooms of conferences. What if Atlas wasn't just unusual, but something fundamentally outside our understanding of natural objects? In the end, what we didn't know about Atlas was a catalog longer than what we did. Its size, its spin, its water content, its tail dynamics, its structural integrity, its origin, its prevalence, and its motion, all cloaked in uncertainty, all resisting clarity. And yet, that ignorance wasn't discouraging, it was invigorating. To stare into the unknown and admit confusion was to acknowledge the vastness of the universe and our own smallness within it. Atlas reminded us that science isn't about neat answers tied up in ribbons. It's about standing before the incomprehensible and asking questions anyway. Every unknown was an invitation, a challenge, a reminder that the cosmos is not ours to master, but ours to witness. And in witnessing, even without answers, we become part of its story. When Atlas entered the conversation, it didn't arrive alone. In many ways, it was impossible to understand this mysterious visitor without looking back at the two that had come before. Oumuamua and Borisov, the first two confirmed interstellar objects, had already carved out their place in astronomical lore. Each had been a shock in its own right, each rewriting the rules in ways no one anticipated. And now, with Atlas as the third entry in this still tiny catalog, the comparisons became unavoidable. To line them up side by side was to see a story of escalating strangeness, a reminder that the universe doesn't play by any single set of rules. It began in 2017, when Oumuamua was first spotted racing past Earth. At the time, it was little more than a faint streak of light, a dot on a survey image that happened to move in the wrong way. But the wrongness was everything. Its orbit was hyperbolic, like Atlas's would later be.
proof that it was a traveler from outside the solar system. That discovery alone was enough to electrify the scientific community. After all, this was the first interstellar object humanity had ever confirmed, but Oumuamua wasn't finished. As astronomers tracked it, they noticed something strange. It wasn't behaving like a comet. There was no tail, no coma, no evidence of outgassing at all, and yet its motion betrayed it. It was accelerating ever so slightly in ways that gravity alone couldn't explain. The lack of visible exhaust left scientists scrambling for explanations. Some suggested it might be shedding hydrogen gas,
Invisible to our instruments. Others proposed that its surface might be made of exotic ices, sublimating in ways we had never seen before. And then came the more radical theories, most famously, the idea that it could be artificial, a relic or probe from another civilization. That leap captured headlines around the world, but even the cautious explanations underscored the point. Oumuamua was unlike anything we had ever seen. 2 years later, in 2019, Borisov arrived to provide a counterpoint. Where Oumuamua had been strange, Borisov seemed almost comforting in its familiarity, at least at first glance. It looked like a comet, acted like a comet, and had a tail like a comet. For many scientists, it was a relief. Here was an interstellar object that fit into a box we understood. But the comfort didn't last. As instruments studied its composition, Borisov revealed its own peculiarities. It was extraordinarily rich in carbon monoxide, far richer than most solar system comets. That imbalance suggested it, too, had formed in an environment very different from our own. If Oumuamua had been the enigmatic outsider and Borisov the reassuringly familiar guest, then both still carried alien signatures in their chemistry. Together, they told us that interstellar visitors weren't anomalies. They were emissaries from places that operated under different rules, chemical recipes written by distant suns. And then came Atlas, the third traveler. If Oumuamua was a silent enigma and Borisov a noisy but familiar presence, Atlas seemed to split the difference. It had a coma and a tail, so it couldn't be dismissed as a sterile rock. Yet it behaved nothing like Borisov or our local comets. Its carbon dioxide dominance set it apart. Its activity was wildly disproportionate to its size, and its tail was faint and hesitant. In comparing the three,
The differences were as striking as the similarities. Each had its own identity, its own fingerprint, and in that diversity lay the larger message. There is no such thing as a typical interstellar object. Each one that crosses our path is a unique window into the infinite variety of planetary systems scattered across the galaxy. What made the comparison so fascinating was how each one broke a different part of the rules. Oumuamua broke the rules of motion, accelerating without visible cause. Borisov broke the rules of chemistry, carrying a surplus of carbon monoxide far beyond our norms. Atlas broke the rules of proportion, exhaling carbon dioxide in volumes that made its size irrelevant. It was as if the universe had staged a trilogy, each act spotlighting a different kind of mystery. And if three objects in less than a decade could each be so strange, what did that say about the countless others drifting unseen in the dark? Were these three the exceptions, or were they the rule? If they were the rule, then our own solar system's comets might actually be the oddities, the tame and predictable cousins of a much wilder family. In the halls of science, these comparisons sparked heated debates. Some argued that the differences were simply the result of small sample size, that with only three examples, randomness was bound to exaggerate contrasts. Others countered that the very extremity of the differences suggested real diversity, not statistical noise. If anything, the interstellar visitors were giving us a crash course in just how chaotic and varied the galaxy could be. They weren't outliers. They were evidence that planetary systems elsewhere produced debris with a far wider range of properties than we ever imagined. The comparison also raised uncomfortable questions about our preparedness. With Oumuamua, we had no chance to study it up close. It was already on its way out by the time we noticed. With Borisov, we had a little more time, but no mission ready to intercept. And now with Atlas, the story was repeating itself. Each interstellar visitor highlighted the gap between our telescopic observations and our ability to truly interact with these objects. If they were as diverse as they seemed, then capturing one, sending a probe to meet it, to sample it, to touch it, would be one of the most valuable scientific opportunities in history. And yet, so far, all we could do was watch them pass, like strangers glimpsed through a window, leaving us with fleeting impressions and unanswered questions. Beyond science, the comparisons seeped into culture and imagination. Oumuamua's odd acceleration inspired novels, documentaries, and endless speculation about alien probes. Borisov's comet-like appearance reassured some, but its alien chemistry still captured headlines about icy bodies from other stars. And Atlas, with its ghostly gas cloud and overwhelming carbon dioxide, was framed as the most haunting yet, a cosmic phantom cloaked in a planetary sized shroud. Each visitor left a mark not only on the scientific record, but on the human imagination, feeding our hunger for stories about what lies beyond. But perhaps the most profound comparison wasn't about chemistry, motion, or appearance. It was about perspective. Oumuamua taught us that interstellar visitors are real, not just theoretical. Borisov taught us that they can resemble the familiar while still carrying alien traits. Atlas taught us that they can be familiar and alien all at once. a paradox that refuses to resolve. Taken together, they sketched a picture of a galaxy teeming with diversity, where every star system leaves behind fragments that drift into the interstellar sea, crossing paths with strangers like us. Each one is a message in a bottle thrown from a distant shore, and so far, every message has been written in a different language. The comparisons also hinted at a sobering truth. Our understanding of planetary formation is provincial. For decades, we've studied the comets of our own solar system, cataloged their properties, and built models of how icy bodies form. But the arrival of these interstellar guests shattered the illusion of universality. Our models describe our solar system, but not necessarily anyone else's. If other systems produce bodies as strange as Oumuamua, Borisov, and Atlas,
then our neighborhood is just one of countless variations. The galaxy is a patchwork of different rules, different outcomes, different chemistries, and with each visitor, we're forced to redraw the boundaries of what's possible. In the end, comparing Atlas to its predecessors was like holding up three puzzle pieces from entirely different sets. Each was fascinating on its own, but none fit neatly with the others. Instead of forming a picture, they formed a challenge to expand our imagination, to accept that the universe is stranger than our models, and to prepare for the next visitor with the humility to expect the unexpected. Umamua.
Borisov, and Atlas weren't just isolated curiosities. They were the opening chapters of a much larger story, one that will continue as long as we keep our eyes on the sky. And if the first three are any indication, the rest of the story will be even stranger. As Atlas blazed its strange path across the solar system, the effort to explain its behavior became a battlefield of theories. The sheer oddness of its activity demanded answers, and yet none seemed to fit comfortably. Every new observation was like a riddle, forcing astronomers to stretch their models to breaking points. The dynamics of Atlas, its outgassing, its motion, its very survival, invited speculation that ranged from cautious science to bold, almost heretical suggestions. In the process, the conversation around Atlas became not just about one object, but about the limits of our imagination when faced with the unfamiliar. The first and most obvious theory focused on outgassing. For comets, the principle is straightforward. Sunlight heats the surface. Frozen ices sublimate into vapor, and the expanding gas carries dust and particles away, forming a coma and a tail. The amount and type of gas released depend on the composition of the nucleus and its distance from the sun.
But Atlas shredded that rulebook. The overwhelming dominance of carbon dioxide, combined with the sheer volume it released, seemed too much for a body of its presumed size. If Atlas were small, then it was expelling material at a rate that should have destroyed it already. If it were large, then why did it appear so faint and elusive? This contradiction forced astronomers to consider that perhaps the gas wasn't being released in the steady, predictable fashion of ordinary comets. Instead, it might be venting in bursts, catastrophic releases from subsurface reservoirs that cracked open under stress. In this model,
Atlas was less a steady snowball and more a pressure cooker, releasing gas in chaotic surges whenever internal stresses became too much. Another school of thought focused on fragmentation. Perhaps Atlas was already in the process of breaking apart, its nucleus fractured into pieces that collectively produced the massive coma we observed. If the body were riddled with fissures, then each fragment could act as its own vent, releasing carbon dioxide in parallel and creating the illusion of impossible activity. This theory gained traction because it offered a way to reconcile the small size of the nucleus with the vast scale of its emissions. But if fragmentation was happening, it was subtle. No clear shards had been spotted, no dramatic breakup like those witnessed with comets near the sun. It was possible that the disintegration was still in its early stages, invisible to our instruments, waiting to play out in spectacular fashion during perihelion. In that sense, the theory carried with it a sense of impending drama. Atlas might not just be a mystery, it might be a ticking time bomb. Some researchers look to the physics of motion for clues. With Oumuamua, the unexplained acceleration had ignited furious debate, and many wondered if Atlas might follow suit. After all,
With so much gas pouring out, its trajectory should show subtle but measurable nudges, like a rocket adjusting its course. Yet so far, Atlas's path remains stubbornly predictable, showing no wild deviations. That raised another puzzle. Was the outgassing balanced in such a way that every jet of carbon dioxide was counteracted by another, leaving the net motion unchanged? If so, the dynamics of its gas release were extraordinarily symmetrical, a level of balance rarely seen in natural systems. The idea of perfect equilibrium seemed unlikely, but the numbers offered no other explanation. This led some to propose that electromagnetic forces might be playing a role, shaping the coma and jets in ways that masked the expected accelerations. The interaction between solar wind, magnetic fields, and Atlas's outflow could, in theory, create effects that mimicked balance. But without direct measurements, the idea remained speculation. One of the more daring hypotheses suggested that Atlas's chemistry itself might be driving unusual dynamics. In this view, the carbon dioxide wasn't just sublimating, it might be reacting with other compounds in ways we hadn't fully modeled. Perhaps the object's ices contained exotic mixtures, frozen under alien conditions, that produced runaway reactions when exposed to sunlight. This could explain the explosive volumes of gas, the strange timing of its tail, and the overall unpredictability of its activity. If true, then Atlas was not merely an interstellar comet, but an interstellar laboratory, carrying out chemical experiments that defied our expectations. For chemists and planetary scientists, this was both terrifying and thrilling. Terrifying because it exposed how incomplete our models were. Thrilling because it hinted at processes we might never have imagined without this chance encounter. And then, inevitably, came the comparisons to Oumuamua's most controversial interpretations. If Oumuamua had sparked and chalked alien probes, could Atlas be subjected to the same? The mainstream consensus rejected the idea. It was venting gas, producing a coma, behaving at least somewhat like a natural body. But the sheer scale of its activity, the perfection of its trajectory, and the balance of its motion gave fuel to fringe voices. Some wondered aloud whether Atlas might not be a single object at all, but a cluster of fragments traveling together, perhaps even deliberately engineered to appear natural. Others speculated about exotic materials unknown to Earth, compositions that could explain its alien chemistry without requiring biology or technology. Even among cautious scientists, there was a quiet acknowledgement that interstellar visitors had a way of forcing us into uncomfortable territory. Every time we declared something impossible, the universe seemed eager to present it to us. What united all the theories was a recognition of how little we really knew. Outgassing, fragmentation, equilibrium, chemistry, even exotic speculation, they all circled the same truth. Atlas was different. Its dynamics were not those of a solar system comet, and our models bent under the strain of trying to make it fit. That realization carried with it a humbling lesson. For decades, we had built our understanding of icy bodies on the assumption that our solar system was typical, but Atlas, like Oumuamua and Borisov before it, showed us that typical is a dangerous word in astronomy. The galaxy is vast, and its diversity defies easy categorization. What seems impossible here might be routine elsewhere, and what seems strange to us might be the norm in another star's backyard. In practical terms, the lack of certainty about Atlas's dynamics made predictions almost impossible. Would it survive perihelion or break apart? Would its emissions grow even more extreme or settle down as it shed its most volatile layers?
Would its trajectory remain steady or suddenly reveal unexplained accelerations once the data caught up? Each possibility had defenders and detractors, and the only way to know was to wait and watch. In that waiting lay the drama. Atlas was a live performance, and every telescope trained on it was part of the audience. The theories were just programs handed out at the door, guesses about how the show might unfold, but the performance itself was in Atlas's hands. And it was a performer that had already proven it didn't follow scripts. As speculation swirled, one conclusion became increasingly clear. Interstellar visitors are not footnotes in astronomy, they are the main event. Each one reveals not just the quirks of a single object, but the broader truth that the galaxy is full of surprises waiting to challenge our assumptions. Atlas's dynamics and the theories they inspired were not just about understanding one comet, they were about preparing ourselves for the countless others we have yet to see. And if three visitors in less than a decade had already left us bewildered, then the future promised a cascade of mysteries beyond imagining. The theories, as wild as some of them seemed, were less about pinning down Atlas than about stretching our imagination far enough to catch up with the universe. And even then, the universe always seemed one step ahead. The discovery of Atlas did something rare in the world of astronomy. It united nearly every major observatory on Earth and beyond into a single, coordinated effort. Normally, telescope time is jealously guarded, scheduled months or even years in advance, with scientists competing fiercely for access. But Atlas wasn't a normal object, and its fleeting passage demanded urgency. It was only the third confirmed interstellar visitor in history, and once it left, it would never return. The clock was ticking, and no one wanted to miss the chance to study it. For a brief moment, rivalries melted away, and what emerged was a global astronomical watch, a kind of emergency response team assembled not for a crisis on Earth, but for a cosmic opportunity. From the high deserts of Chile to the volcanic peaks of Hawaii, from space-based telescopes orbiting hundreds of miles above Earth to massive observatories parked at distant Lagrange points,
The eyes of humanity turned toward this alien traveler. The Atlas survey that had first spotted it continued its monitoring, but now it had company. Hubble focused its powerful optics, Gemini North trained its adaptive mirrors, and the James Webb Space Telescope prepared its infrared sensors for the chemical feast. Even smaller facilities joined in, university observatories and amateur astronomers contributing valuable data points that filled in the gaps. It wasn't just professional scientists who wanted a piece of Atlas, it was everyone with access to a lens and a passion for the sky. The coordination was extraordinary.
networks of astronomers shared real time updates, pooling their findings instead of hoarding them. Observing schedules were rearranged, priority lists rewritten, all to give Atlas the stage it demanded. For many scientists, it was the first time they had seen such a collective response, a recognition that some events are too big for individual projects and must be treated as global phenomena. This was not just a discovery, it was a moment in human history, and the community knew it. NASA's Swift Observatory was one of the first space based instruments to lock on, capturing ultraviolet images that revealed new details about the composition of Atlas's coma. Meanwhile, the James Webb Space Telescope turned its infrared gaze toward the object, confirming the overwhelming presence of carbon dioxide and puzzlingly faint traces of water. The Hubble Space Telescope provided visual clarity, resolving the diffuse coma and hinting at the scale of its emissions. On the ground, Gemini North in Hawaii and the Very Large Telescope in Chile both contributed detailed spectra, each adding a piece to the growing puzzle. The data flowed like a torrent, filling servers and hard drives.
Demanding constant analysis as researchers raced to keep up. What made the global watch particularly compelling was the looming challenge of solar conjunction. Everyone knew that Atlas would soon pass behind the sun, vanishing from Earth's view for months, just as it reached its most dramatic phase. That blackout made every hour of observation beforehand more precious. Scientists described it as a kind of sprint, a race to gather as much as possible before the curtain fell. The sense of urgency drove cooperation to new heights. If one team had cloudy skies, another stepped in from a different continent. If one telescope went offline,
Another picked up the slack. It was a relay race across the globe. The baton passed from night to night, hemisphere to hemisphere, as humanity collectively tracked the stranger from the stars. Even Mars was drawn into the effort. As Atlas prepared to make a close pass by the red planet, mission planners scrambled to see whether orbiters like the Mars Reconnaissance Orbiter or ESA's Trace Gas Orbiter could catch images. It was a tantalizing possibility, a view of an interstellar object from another world, a perspective Earth based telescopes could never achieve. Though technical limitations and mission priorities made it uncertain,
the very fact that such coordination was attempted spoke volumes. Atlas had become more than just an astronomical curiosity. It was a test of how quickly humanity could pivot its resources to meet an unplanned cosmic event. Behind the scenes, the watch carried an emotional weight. For many astronomers, this was the chance of a lifetime, the kind of discovery they might have dreamed of as students but never expected to witness in their careers. The odds of catching an interstellar object are slim, and yet here was the third in less than a decade, each more peculiar than the last. The sense of history hung over every observation, every data file. To miss an opportunity to contribute was to risk being left out of a story that would be told for generations. Graduate students worked through nights, professors delayed vacations, technicians and engineers bent schedules to keep instruments pointed and running. Atlas had become a global obsession, and no one wanted to blink. The data sharing platforms lit up with activity. Slack channels, mailing lists, and collaborative networks buzzed with updates, images, spectra, and speculation. Some of the discussions bordered on frantic, with new findings raising more questions than they answered. A faint detection of water here, an odd fluctuation in brightness there, a suggestion of fragmentation whispered across continents. Theories were born, debated, and discarded in real time, the collective mind of astronomy grappling with a riddle too big for any single group to solve. For many participants, it was the most alive science had ever felt, a global puzzle unfolding in the present tense, no textbooks, no precedents, just the raw unknown. The watch wasn't without challenges. Cloud cover ruined some nights, instrument malfunctions delayed others, and the sheer volume of data overwhelmed analysis pipelines.
yet the setbacks only underscored the resilience of the network. When one observatory faltered, another filled the gap. When one data set proved inconclusive, another provided clarity. The redundancies of global science became its strength, each failure balanced by success elsewhere. The image that emerged wasn't just of Atlas, but of humanity itself, a species capable of setting aside boundaries and working as one when the cosmos beckons. And still, for all the effort, Atlas remained elusive. Its coma masked the nucleus, its tail flickered unpredictably, its chemistry defied logic.
The global watch was less about solving the mystery than about documenting it, capturing every nuance so that future generations could study it long after Atlas had vanished into the dark. In that sense, the observations were like a time capsule, a record of an encounter that would never happen again. The knowledge that this was our only chance lent every photon, every spectrum, every faint smear of light on a CCD the weight of history. The watch also revealed something deeper about our place in the universe. Atlas was not a threat, not an asteroid on a collision course, not a harbinger of doom. It was simply passing by, indifferent to us, a wanderer on a path that happened to intersect with ours for a brief moment, and yet that indifference was precisely what made it so profound. We had mobilized the full power of our species' scientific apparatus, not because Atlas threatened us, but because it intrigued us. In its passing, it reminded us that curiosity is our most defining trait, that the urge to look outward, to understand, to connect with the unknown, is what binds us together. When Atlas finally slipped behind the sun, leaving us blind to its fate, the global watch did not end. Plans were already in place to resume observations the moment it reemerged.
Telescopes were cued, schedules prepared, eyes ready. Whatever had happened during those months of invisibility, whether Atlas had fractured, survived, or transformed, the world would be waiting to bear witness. The story wasn't finished. It was merely paused, like a book closed at its climax, the next chapter waiting just beyond the horizon of the sun. As the world's telescopes strained to capture every fleeting detail of Atlas, one question began to rise above all others, whispered first in side conversations and later asked aloud in conference calls and journal articles. Could we chase it? For decades,
Science fiction had dreamed of humanity reaching out to touch the visitors from beyond, sending spacecraft to intercept alien debris drifting through our neighborhood. Now, with Atlas blazing its ghostly trail across the solar system, that dream felt tantalizingly close. The object wasn't on a collision course, it wasn't threatening Earth, but it carried something even more valuable, the promise of knowledge. If Oumuamua had eluded us and Borisov had been too brief, perhaps Atlas might be the one we could actually catch. The idea of chasing an interstellar object isn't new. After the shock of Oumuamua's appearance in 2017, space agencies began sketching hypothetical missions, interstellar interceptors that could launch on short notice and pursue these rare visitors. NASA even studied concepts like the Comet Interceptor mission, a kind of spacecraft on standby that could be parked in a holding orbit and then dispatched the moment a target appeared. The European Space Agency began developing a similar plan, envisioning a probe that could lie in wait near Lagrange points, ready to spring into action when the next stranger wandered by. But these were only ideas, concepts on paper, years away from reality. Atlas, inconveniently, was here now.
the first challenge was speed. Interstellar objects move fast. By definition, they are on hyperbolic trajectories, entering our system with immense velocity, never to return. Oumuamua zipped through so quickly that by the time we realized what it was already gone. Borisov gave us more time, but its trajectory still placed it beyond the reach of any spacecraft we could launch on short notice. Atlas was no different. Calculations showed it would be traveling tens of kilometers per second, speeds far beyond the grasp of our current rockets, if we hoped to intercept it in time.
Even with the most powerful launch vehicles available, the Falcon Heavy, the SLS, or future designs like Starship, the required Delta V pushed the boundaries of what was possible. It wasn't just about launching fast, it was about launching soon, and Atlas's window was closing. Still, the allure of the challenge was irresistible. Engineers began sketching scenarios. What if we used a gravity assist from Jupiter, slingshotting a spacecraft into a chase trajectory? What if we mounted a probe on a heavy lift rocket and aimed directly for an intercept point in deep space? Some proposals involved nuclear powered propulsion, ion drives,
Or even solar sails, exotic technologies that could, in theory, build the speed needed to catch an interstellar traveler. Each scenario was bold, imaginative, and almost certainly impractical on the timescale Atlas demanded. Yet the very act of asking the question pushed the boundaries of thought. For perhaps the first time, the idea of pursuing an interstellar object wasn't just speculation, it was a real engineering problem, grounded in the presence of a target just beyond our reach. The science payoff of a successful chase was staggering. Imagine flying alongside Atlas, sending back images not of a fuzzy coma, but of the nucleus itself. Imagine sampling its gases directly, measuring the chemistry of its alien ices without the filter of distance. Imagine scooping up dust grains released from its surface, tiny relics of a star system light years away, carried back for analysis in Earth's laboratories. The chance to study matter unaltered by billions of years in our own solar system was almost beyond comprehension. It would be like receiving a time capsule from another world, one that might tell us how planets form, what conditions exist elsewhere, and how our own origins fit into the wider story of the galaxy. No telescope, no matter how powerful, could match the intimacy of being there, of touching an interstellar object directly. But against the dream stood reality. To build and launch a spacecraft capable of such a chase would take years, not months. By the time we had anything ready, Atlas would be gone, lost to the void, another mystery we could only watch from afar. The frustration was palpable. Scientists spoke of technology heartbreak, the agony of knowing that the tools to answer our questions existed in theory, but not yet in practice. For many, it reinforced the urgency of building an interstellar interceptor now, before the next visitor arrived. If three had already come in less than a decade, who knew how many more might pass by in the years ahead? The lesson of Atlas was clear. We had to be ready because the universe would not wait for us to catch up. There were even whispers of wilder ideas. Some suggested piggybacking on existing missions, rerouting probes already in space to swing past Atlas. Could New Horizons, the spacecraft that had already flown by Pluto and Arrokoth, be nudged onto a trajectory to meet it? The answer was no. Its path and speed didn't align. Others dreamed of leveraging experimental propulsion methods like laser-driven light sails to fling small probes toward Atlas at incredible velocities. These concepts were speculative, barely beyond the drawing board, but they captured the imagination. For the first time, the notion of chasing an interstellar visitor didn't feel like science fiction. It felt like a challenge. Difficult, yes, but not impossible forever. The global astronomical watch added weight to the question. With so many telescopes focused on Atlas, the flow of data painted a vivid picture of what we were missing. Every spectrum, every image was a reminder of the gulf between observing from afar and being there. The more we learned,
The more we longed to send a spacecraft, and the more painful the absence of one became. For some in the scientific community, it was a turning point. Oumuamua had been a shock, Borisov a confirmation, but Atlas was a call to action. If we didn't build the capacity to chase these objects, we would continue to let them slip through our fingers, forever watching, but never touching. There was also the tantalizing question of discovery. If we could chase an object like Atlas, what might we find? Would its chemistry confirm our theories or upend them completely? Would its surface be pockmarked like a comet or something entirely new? Could it even carry complex organic compounds, the raw ingredients of life, forged in a distant system and carried across interstellar space? The possibilities stretched beyond science into philosophy. To intercept an interstellar object was to hold in our hands a piece of another star, a fragment of the galaxy's endless creativity. The thought alone was enough to make the question of could we chase it echo louder and louder in the halls of astronomy. For now, the answer remained no. We could not chase Atlas. It was too fast, too fleeting, too far. But in the act of asking, we planted seeds. The engineers sketching intercept trajectories.
the scientists advocating for standby probes, the dreamers envisioning solar sails, all were preparing us for the next time because there would be a next time. The galaxy was full of wanderers, and if three had already come, more were waiting. When the next one appeared, perhaps we would be ready. Perhaps the heartbreak of Atlas would become the spark that drove us to build, to prepare, to chase. And when that day came, humanity's reach would extend not just across our own solar system, but into the vast interstellar sea. The legacy of Atlas was never going to be measured only in data charts, telescope logs, or published papers. Those were the immediate artifacts, the tangible record of its brief visit. But the true legacy, the one that would echo for decades, was something far larger. Atlas was a mirror, reflecting not only the mysteries of the cosmos, but also the ways in which humanity responds to the unknown. It was the third interstellar traveler we had ever seen, and in that simple fact, it became part of a lineage, a sequence of encounters that reshaped our view of the universe and our place within it. Long after Atlas had slipped back into the dark, its impact would remain, woven into the story of how we, as a species, learned to look outward with new eyes.
One piece of that legacy was cultural. Like Oumuamua before it, Atlas captivated the public imagination in ways few astronomical discoveries managed to do. Its ghostly form, its planetary sized shroud of carbon dioxide, its sheer alien chemistry, all of it carried a cinematic quality that headlines and documentaries eagerly embraced. Images of Atlas appeared in newspapers, science magazines, and late night television, framed as a cosmic phantom haunting our solar system. For the general public, it wasn't just a scientific anomaly, it was a story.
One that tapped into our deepest curiosity about life beyond Earth and the possibility of alien worlds. That cultural spark mattered. When the public is enthralled, funding follows, and the political will to support ambitious missions grows stronger. In that sense, Atlas was more than an object of study. It was an advocate for the future of space exploration, but the scientific legacy was equally profound. Atlas's chemistry shattered the illusion that interstellar objects might conform to familiar templates. Oumuamua had been silent and inert, Borisov noisy but comet-like, and Atlas something in between, yet unlike either.
The overwhelming dominance of carbon dioxide, the faint traces of water, the strange proportions of its activity, all of it forced planetary scientists to admit that our models were provincial. We had built theories based on solar system comets, but those theories couldn't stretch far enough to encompass Atlas. It demanded new models, new thinking, and in that demand, it propelled the field forward. For graduate students writing their dissertations, for theorists testing their simulations, for engineers dreaming of intercept missions, Atlas became a touchstone, a case study in humility before the cosmos.
Another part of its legacy was institutional. The global astronomical watch that had sprung up around Atlas showed what was possible when scientists coordinated across borders, telescopes in different hemispheres, agencies with competing agendas, even amateur astronomers with modest equipment. All had joined in a shared effort to document the alien visitor. That spirit of cooperation left its mark. Many of the networks formed during the Atlas campaign continued afterward, laying the groundwork for future collaborations. If Oumuamua had shocked us into realizing interstellar objects were real, and Borisov had proven they could be studied in detail, then Atlas showed us how to respond as a species. Its legacy was not only in the data it gave us, but in the precedent it set. The recognition that when the universe drops a mystery at our doorstep, we must come together to meet it. Atlas also left behind a legacy of urgency. The frustration of watching it pass by without the possibility of interception fuel calls for readiness. Scientists pointed to Atlas in proposals for interstellar interceptor missions, using it as Exhibit A in the argument that we could not afford to be unprepared again. Already, agencies were sketching plans for spacecraft that could lie in wait, ready to chase the next visitor. Atlas became the rallying cry, the reminder that opportunities slip away if we hesitate. Its legacy was written not only in the questions it raised, but in the determination it inspired to ensure that the next time we would do more than watch. And yet, perhaps the deepest legacy of Atlas was philosophical. For centuries, humanity had stared at the stars and wondered what lay beyond. Now, pieces of that beyond were coming to us, drifting into our solar system, carrying the fingerprints of alien suns. Atlas, with its bizarre chemistry and ghostly shroud, was proof that the galaxy is not homogeneous, that every star system writes its own story in ice and rock. It reminded us that our solar system is not the standard by which others should be measured, but simply one variation among countless others. The legacy of Atlas, then, was the widening of perspective, the shift from thinking of our neighborhood as the template to seeing it as one small note in a symphony far larger than we can yet hear. The legacy also extended into art and imagination. Writers, filmmakers, and musicians seized on the imagery of Atlas, weaving it into narratives of alien messengers, cosmic omens, and interstellar mysteries. In that sense, Atlas joined the ranks of Halley's comet, Oumuamua, and other celestial phenomena that leap from science into myth. Its story became a canvas onto which human creativity could project fears, hopes, and speculations. Every culture that looked up at Atlas during its brief passage added its own layer of meaning, transforming a physical event into a shared mythic moment. Centuries from now, when the data may be forgotten, the stories may remain. Of course, part of Atlas's legacy was the unfinished business it left behind.
Its nucleus remained unseen, its exact size uncertain, its internal structure unknown. The contradiction of its water content, present in faint hints, absent in stronger data, was never resolved. Whether it fragmented behind the sun or survived intact, we might never know for sure. Those gaps were frustrating in the moment, but in the long run, they became part of its gift. By leaving us with unanswered questions, Atlas ensured that curiosity would linger, driving future scientists to seek out the next object with even greater determination. Sometimes the greatest legacy is not in the answers given, but in the hunger left behind.
And there was one final, subtler legacy. Atlas reminded us that the universe is not static, not frozen in textbooks or confined to the familiar orbits of our planets. It is dynamic, surprising, and full of visitors that come unannounced. To live in such a universe is to accept uncertainty, to embrace wonder, to admit that the cosmos will always be stranger than we expect. In that sense, the legacy of Atlas was not just scientific or cultural, it was emotional. It rekindled awe. In a world often weighed down by cynicism, division, and routine, Atlas was a reminder of how small we are and how vast the unknown remains. That feeling, more than any data set, may be its greatest gift. So when the story of Atlas is told, it won't end with its vanishing into the dark. It will continue in the missions it inspired, the models it reshaped, the collaborations it fostered, and the imaginations it ignited. Its legacy will echo in every future interstellar object we study, every spacecraft we launch in pursuit of one, every child who looks at the stars and dreams of what else drifts out there. Atlas came from the unknown, lingered for a moment, and then returned to it. But in that brief encounter, it left us changed, and that perhaps is the truest legacy of all. From the moment Atlas was first spotted, the fascination it stirred wasn't limited to astronomers hunched over data streams. It bled into every corner of human curiosity, into the conversations of people who had never pointed a telescope at the sky, into forums, classrooms, coffee shops, and even late night arguments among friends. There is something irresistible about a visitor from another star. something that ignites the imagination in ways ordinary discoveries rarely can. Atlas wasn't just a comet, it was a messenger. And as with all messengers, speculation about its meaning became as important as the facts of its existence.
Much of the fascination lay in its strangeness. The images of its coma, a hazy cloud so vast it dwarfed planets, spread quickly across the internet. People were captivated by the idea that such a small object could create such an immense shroud, a reminder that the cosmos doesn't follow the proportions we expect. News outlets framed it as a phantom comet, a ghostly wanderer whose chemistry and behavior seemed fundamentally alien. That ghostliness gave Atlas an aura of mystery that reached beyond science. To some, it felt like a harbinger, a cosmic omen drifting silently through our skies. To others, it was a symbol of the unknown.
Proof that the universe still had the power to surprise us. Speculation grew quickly, and as with Oumuamua before it, not all of it stayed within the bounds of science. Conspiracy theories bloomed, claiming Atlas was not a comet at all, but a disguised spacecraft, perhaps abandoned, perhaps still active. Vlogs and podcasts spun narratives of alien probes watching us, slipping through our solar system under the cover of natural phenomena. Some claimed its perfect balance of outgassing, its symmetrical emissions, were evidence of artificial control. Others latched onto its eerie silence in terms of rotation, wondering if such steadiness could truly be natural. These ideas rarely held up under scrutiny, but their popularity spoke volumes. Whenever the cosmos presents us with a mystery, we cannot resist projecting our deepest hopes and fears onto it. Even within the scientific community, speculation thrived. Was Atlas the fragment of a shattered world, a piece of an alien planet's outer crust blown into space by some ancient catastrophe? Was it a relic from the early days of its parent system, carrying with it the frozen chemistry of worlds that never fully formed? Could its bizarre dominance of carbon dioxide hint at an environment radically different from ours, perhaps a solar system where water was scarce but carbon rich ices flourished? Each theory was more exotic than the last, but all shared one truth. Atlas reminded us that we know almost nothing about the diversity of planetary systems beyond our own. Every speculation was, in some way, a mirror of our ignorance. Fascination with Atlas also tapped into deeper human stories. For centuries, comets were seen as omens, bringers of change, harbingers of upheaval. Kings trembled, commoners prayed, wars were predicted, and plagues blamed on these luminous wanderers in the night. That ancient instinct, though tempered by science, still lingered. When Atlas appeared, glowing faintly in the dark, the cultural memory of comets as signs of destiny resurfaced. Some wrote poems about it, others painted it, and many simply stared up, wondering what it meant that something from so far away had chosen, for reasons beyond our comprehension, to pass through our skies. The speculation grew wilder as Atlas approached the sun. Would it survive? Would it break apart, scattering fragments that might one day drift near Earth?
Would it reveal even stranger chemistry under the heat, perhaps outgassing substances we had never seen in a comet before? Social media lit up with countdowns, live streams, and watch parties. For a brief moment, people across the globe were united in anticipation, watching the skies not for fear, but for wonder. Atlas wasn't threatening us, but it commanded our attention nonetheless. It was a reminder that even in an age of distraction, the universe can still make us look up. Speculation about life inevitably entered the conversation. If Atlas carried complex organic compounds,
Could they have formed the building blocks of biology in its parent system? Could objects like it scatter such compounds across the galaxy, seeding the potential for life wherever they landed? The idea wasn't far fetched. Many scientists already believe comets in our own solar system may have delivered essential ingredients for life on Earth. If Atlas carried its own version of those ingredients, then it became more than a curiosity. It became a participant in the great story of life's origins, a traveler carrying the raw materials of biology across interstellar space. That possibility elevated fascination into reverence. Atlas wasn't alive.
But it might carry the seeds of life within it. Of course, not all fascination was grand. For many, it was simply the thrill of the chase, the joy of witnessing something rare and fleeting. Amateur astronomers stayed up late to catch glimpses of its faint glow. Parents showed their children images online, and classrooms used it as a way to spark interest in science. The fact that Atlas came from another star system gave everyone a sense of participation in something extraordinary. You didn't need to be an expert to appreciate it. You only needed to know that for a brief moment, our solar system was hosting a visitor from the wider galaxy.
That alone was enough to stir awe. The speculative energy also had a practical effect. By imagining what Atlas could be, people began to demand more from our technology. Why couldn't we chase it? Why didn't we have spacecraft ready? What if the next visitor was even stranger? These questions, voiced not just by scientists, but by ordinary people, created momentum. Fascination became pressure. Speculation became advocacy. Space agencies took note, weaving the lessons of Atlas into proposals for intercept missions and new observatories. The very act of wondering what Atlas might be was pushing humanity toward readiness for the next one. At its core, the fascination and speculation surrounding Atlas spoke to something timeless in us. We are a species defined by curiosity, by the refusal to accept ignorance as permanent. Every strange object becomes a canvas for our imagination, every unknown a stage for our storytelling. Atlas reminded us of that in the most dramatic way. It arrived unannounced, defied explanation, and left us grasping for meaning. In doing so, it became more than just a comet. It became a story we told ourselves about the universe, about the unknown, about our place in the vastness of space. And maybe that is the deepest reason for the fascination.
Atlas was not here for us. It didn't choose to pass our way, didn't seek to teach or to communicate. It was indifferent, a shard of ice and rock drifting on a path shaped by forces far older and larger than us. Yet, in its indifference, it gave us a gift. It reminded us that the universe is alive with mystery, that we are surrounded by wonders we cannot yet grasp. The fascination was not in Atlas itself, but in what it revealed about us, that even in an age of advanced science, our first instinct when confronted with the unknown is to imagine, to speculate, to dream. And in those dreams, we find both the seeds of discovery and the soul of our species. If Atlas taught us anything, it was that interstellar visitors are not rare flukes, not once in a lifetime miracles, but recurring guests who slip silently through our neighborhood far more often than we once believed. For most of human history, the idea that a comet or asteroid from another star system could wander into ours was pure theory, a possibility buried in equations but never observed. Then came Oumuamua in 2017, Borisov in 2019, and Atlas not long after, three interstellar messengers in less than a decade. That sudden burst of encounters was not coincidence, it was revelation. It told us that the galaxy is constantly exchanging fragments, that planetary systems are not isolated bubbles, but part of a larger cosmic ecosystem, their debris and mixing and mingling across light years. The future of interstellar visitors, then, is not in doubt. More will come. The only question is whether we will be ready. Astronomers now believe that countless interstellar objects drift through our solar system every year, most too small or faint for us to detect. Our instruments simply aren't sensitive enough to catch them. Oumuamua, Borisov, and Atlas were the rare ones large and bright enough to be spotted, but they may represent only the tip of the iceberg. As survey telescopes grow more powerful, The number we detect is expected to surge. The Vera Rubin Observatory, once fully operational, will scan the sky with unprecedented depth and speed, capable of spotting faint, fast moving objects that would have eluded us before. Many astronomers predict that within the next decade, we could be discovering interstellar visitors regularly, not once every few years, but several times a year. What once seemed extraordinary will become routine, and with each new discovery,
Our picture of the galaxy's diversity will sharpen. The future also lies in preparation. The heartbreak of Oumuamua, the frustration of Borisov, and the urgency of Atlas all hammered home the same lesson. Telescopes can only take us so far. If we want real answers, we must send spacecraft. That realization has already taken root. Space agencies are designing missions specifically to intercept the next interstellar visitor. ESA's Comet Interceptor, scheduled for launch later this decade, will be stationed in a holding orbit at the L2 Lagrange point, ready to sprint toward the first promising target that appears. NASA has its own concepts for rapid response missions, including designs that could launch within weeks of detection, powered by advanced propulsion systems capable of catching even the fastest travelers. For the first time in history, humanity is planning not just to observe interstellar visitors, but to meet them face to face. The science payoff of such missions is almost incalculable. Every interstellar object carries within it the chemistry of another star system, frozen into its ices and minerals. By touching one, by sampling its gases, or collecting its dust, we could study matter forged under conditions alien to our own. We could test whether the building blocks of life are common across the galaxy, whether other systems produce the same organics we see in our comets, or whether they follow entirely different recipes. We could probe their structure, their magnetism, their internal strength, and in doing so, learn not only about distant worlds, but about the processes that shape planets everywhere. Each visitor is a scientific time capsule, carrying messages from systems we may never reach otherwise. The future of interstellar visitors is the future of cosmic archaeology, each one a shard of history, waiting to be read. But the future isn't just about science, it's about imagination. Every new visitor will inspire speculation, just as Oumuamua did with its mysterious acceleration, just as Atlas did with its carbon dioxide shroud. Some will be ordinary, behaving like comets or asteroids we already understand, and even those will be precious. Others will be strange, bending the rules, forcing us to rewrite theories, and perhaps someday one will be extraordinary beyond all measure, carrying anomalies we cannot explain with any natural model. The possibility that one of these objects could be artificial, debris from an alien civilization, a probe, a relic, will always hover in the background, unproven but irresistible. Even if most are mundane, the fact that we are now able to detect them means the door is open to the greatest discovery in human history. The future of interstellar visitors is, in a very real sense, the future of the search for extraterrestrial intelligence, not through signals in the sky, but through objects passing silently through our own backyard. Another part of the future lies in policy and cooperation. Interstellar visitors will not respect borders. They will not appear over one nation's skies or belong to any single agency. Their study will demand the kind of global collaboration we glimpsed with Atlas, but on a larger, more organized scale. Networks must be built not just for sharing data, but for coordinating missions, for pooling resources, for ensuring that when the next one comes, the whole world can respond as one. Atlas hinted at what is possible when humanity works together. The future will demand it. In the same way that climate change or planetary defense requires global cooperation, so too will the study of interstellar visitors. They are not just scientific curiosities, they are shared heritage, pieces of the galaxy drifting through our common sky. The pace of discovery will also force a cultural shift. Once comets were rare enough to inspire myths and omens. Now, with surveys like Atlas and Pan-STARRS, we track dozens at any given time. Interstellar objects will likely follow the same path. What was once shocking will become familiar. But familiarity does not mean insignificance. If anything, the normalization of interstellar discoveries will deepen our sense of the galaxy's richness, reminding us that we are part of a cosmic web of exchange, our system constantly interacting with others. Each detection will be a reminder that we are not isolated, not alone.
but embedded in a larger story of matter flowing between stars. And yet, no matter how common they become, some will still stand out. The first time we intercept one, the first time we collect a sample, bring it home, the first time we discover organics or minerals that don't exist in our solar system, those moments will be milestones in human history. They will change textbooks, inspire generations, and reshape our understanding of what it means to live in a galaxy full of planets and stars. The future of interstellar visitors is, at its heart, the future of humility. The acceptance that our solar system is just one example, one note in a vast cosmic symphony. And the more visitors we see, the more we will realize how diverse, how surprising, how endlessly creative that symphony is. Perhaps the most exciting prospect is that the future may already be arriving faster than we expect. If Oumuamua, Borisov, and Atlas came within just a few years of each other, what does that suggest about the decades to come? Will we soon be tracking dozens, hundreds, and if so, what strange chemistry, what baffling shapes, what haunting mysteries are waiting just beyond the reach of our telescopes? The truth is, we don't know, but that ignorance is itself the promise. The future of interstellar visitors is not about certainty, it is about wonder, about the endless horizon of what remains undiscovered. Atlas may have passed, but it left behind more than data. It left a glimpse of the road ahead, a road filled with wanderers yet to come. Each one will carry with it the chance to expand our knowledge, to ignite our imagination, to remind us that the universe is far richer than we dare to believe. The future of interstellar visitors is the future of discovery itself. And with each passing shard of alien rock or ice, humanity will take another step into the grand story of the stars. As Atlas fades into the dark,
Slipping back toward the void it came from, what remains is not the sight of a glowing coma or the trace of its carbon dioxide shroud, but the impression it left on us. In the end, interstellar visitors are not ours to keep. They come without warning, linger for a heartbeat in cosmic time, and then vanish forever. What we carry with us is not the object itself, but the way it changes how we see the universe and how we see ourselves. Atlas, like Oumuamua and Borisov before it, was a reminder that the galaxy is not some distant abstraction. It is present, active, and intertwined with us in ways we are only beginning to understand. Final thoughts on Atlas can't be separated from the emotions it stirred: awe, confusion, frustration, wonder. They all collided in the brief months we tracked it. Scientists were awed by its chemistry, baffled by its behavior, frustrated by the limits of their instruments, and inspired by the glimpse it offered of distant star systems. The public was entranced by its ghostly beauty, captivated by the idea of a traveler from another world. Together, those reactions formed a chorus of fascination that echoed far beyond the observatories. Atlas wasn't just a comet, it was an event, a shared moment in human history.
a reminder that no matter how much we think we know, the universe still holds surprises that can stop us in our tracks. One of the lasting lessons of Atlas is humility. We like to imagine that our models are complete, that the rules we've written for comets and asteroids apply everywhere. But Atlas refused to obey. It spewed carbon dioxide in volumes that defied logic, teased us with inconsistent traces of water, masked its nucleus behind a veil we couldn't penetrate. It was a living contradiction, a cosmic puzzle that didn't fit into our categories. And that is precisely why it mattered.
Science doesn't advance when nature behaves as expected. It advances when something breaks the rules. Atlas broke them with flair, and in doing so, it forced us to expand our imagination. Its legacy is the realization that the cosmos is far stranger than our textbooks, and that strangeness is the point. Another final reflection lies in urgency. The three interstellar visitors we've seen so far, Oumuamua, Borisov, and Atlas, arrived unexpectedly and left us scrambling. Each one left behind the same bitter truth. We weren't ready. We weren't ready to intercept them, to sample them, to study them up close. All we could do was watch from afar, collecting what scraps of data we could before they slipped away. That failure is painful, but it also clarifies the path ahead. If we want to seize the opportunities the universe offers, we need to be prepared. We need spacecraft waiting in ambush, propulsion systems ready to launch, missions designed not for decades of planning, but for immediate response. Atlas, by frustrating us, made that truth impossible to ignore. The outro of its story is not an ending, but a call to action. Be ready, because the universe will not slow down for us. But perhaps the deepest final thought is about perspective. Atlas was small,
Perhaps only a few kilometers across, maybe even less, and yet, for a brief time, it commanded the attention of our entire species. Telescopes worldwide turned toward it, engineers dreamed of chasing it, artists painted it, children imagined what it might mean. That disproportion between size and impact is the essence of astronomy. Tiny points of light, distant specks, faint streaks across the sky. They carry within them the power to reframe how we understand everything. Atlas reminded us of that. It was a mountain sized rock, yes, but it was also a mirror in which we saw our hunger for knowledge, our capacity for wonder, and our refusal to stop asking questions. In the broader story of interstellar visitors, Atlas is still only a beginning. Oumuamua taught us that interstellar objects exist. Borisov taught us that they can resemble comets while still carrying alien chemistry. Atlas taught us that they can be stranger still, defying both categories at once. Three objects, three lessons, three reminders that the universe is more diverse than we dared to imagine. What comes next will be shaped by those lessons. The next visitor we discover might be ordinary, or it might be extraordinary beyond anything we've seen, but whatever it is,
we will see it differently because Atlas passed our way. That is the gift of these encounters, not just the data, but the change in perspective they leave behind. And then there is the human side of the outro. The fascination with Atlas will not fade quickly. It will live on in classrooms where students first learn about interstellar objects, in research papers that cite its chemistry, in missions that are justified by its example. It will live on in the imaginations of people who saw it not as a ball of ice and gas, but as a messenger, a wanderer, a reminder that we are part of something vast.
the outro of Atlas's story is written not in its trajectory, but in us, in the way we talk about it, the way we dream about it, the way we use it to fuel our next steps into the cosmos. For those who watched it closely, Atlas also carried a personal outro. Astronomers who spent sleepless nights tracking it, who rearranged schedules and lives to follow its fleeting glow, felt a sense of intimacy with the object that data alone cannot capture. They spoke of it as though it were a guest, a visitor that had stayed briefly in their lives before leaving. That sense of personal connection is not easily quantified, but it matters. It matters because it humanizes science, reminding us that at its core, astronomy is not just equations and spectra. It is people looking up, feeling awe, and wanting to understand. Atlas, in its brief visit, reminded us of the emotional side of science, the joy and frustration and wonder that drive us forward. And so, as Atlas drifts back into the dark, the outro of its story is both an ending and a beginning. An ending because its passage through our solar system is over. We will not see it again, not in our lifetimes, not ever, but a beginning because the questions it left behind will shape the future. Missions will be built because of it. Theories will be rewritten in response to it. Children will dream of space because of it. In that sense, Atlas is still here, not in the sky, but in us. Its final gift is the reminder that the universe is alive with wonder, and that our job is not to tame it, but to keep chasing it, question after question, mystery after mystery. The outro of Atlas's tale, then, is not a goodbye. It is a promise that more will come, that the universe will continue to send us messengers from beyond, that each one will challenge us, frustrate us, inspire us, a promise that as long as we keep looking up,
The sky will keep surprising us. Atlas is gone, but the story it began is only just unfolding. And when the next interstellar traveler appears, we will remember this ghostly visitor, this phantom comet, this enigma of carbon dioxide and mystery. We will remember Atlas, and we will be ready to listen. In the end, Atlas was never really ours to claim. It came from somewhere we cannot yet map, from a star system we will never know, carrying with it the chemistry and the secrets of another corner of the galaxy. For a brief moment, it wandered through our skies, and then it was gone, racing back into the dark, beyond the reach of every telescope, beyond the grasp of every spacecraft. All we can do is hold on to the memory of that fleeting encounter, the data it left behind, and the questions that now burn brighter than the answers we found. And maybe that is the truest measure of its importance. Not that it solved mysteries, but that it gave us new ones. Atlas left us staring into the unknown, and that is exactly what the greatest discoveries always do. The story of Atlas is not just about a comet or an object of ice and dust. It is about us, about humanity's reaction when faced with the unexpected. When something alien crossed into our solar system, we did not look away. We watched.
we measured, we argued, we imagined. Atlas reminded us that wonder is still alive, that even in an age of endless distractions and constant noise, the universe can still silence us with something so strange and beautiful that we cannot help but pay attention. It showed us that science is not just about facts, but about curiosity, about leaning into the mysteries rather than shying away from them. But there is also a bittersweet edge to the conclusion of Atlas's tale. We were not ready. We had no spacecraft prepared to chase it, no instruments close enough to peel back its layers, no mission that could bring us face to face with its nucleus.
We watched it pass by, helpless, knowing that its secrets would remain locked within it forever. That sting of unpreparedness is part of the lesson it leaves behind. The next time, we must do better. The next time, we cannot settle for watching from afar. Atlas, by eluding us, forced us to admit the limits of our reach, and that humility is itself a gift. It tells us where we must go next, what we must build, and how we must prepare. As Atlas drifts back into the void, it leaves us with a paradox. On one hand, it was small, just a fragment, a shard, perhaps only a few kilometers across. On the other, it was immense in its impact.
It reshaped models, inspired missions, sparked debates, and rekindled our sense of wonder. It reminded us that the universe is not distant or static, but alive, dynamic, and constantly touching us with pieces of itself. Every interstellar visitor is proof that the galaxy is in motion, that systems are not sealed off but open, that we live in a cosmos of exchange and connection. Atlas was a traveler, but it was also a thread in that larger web, a reminder that our solar system is part of a story far bigger than we can yet comprehend. So the conclusion is this: Atlas was not the end of something, but the beginning.
It was one more chapter in a story that is still being written, a story of interstellar wanderers and the humans who dare to chase them. It leaves us with hope as much as with mystery. Hope that the next visitor will arrive soon. Hope that we will be ready when it does. Hope that somewhere out there, drifting among the stars, countless others are on their way. Atlas may be gone, but the universe will send more. And when it does, we will remember the ghostly traveler that slipped silently through our skies and left us forever changed.